In this third video on integrated rates, we will define what is meant by the term half-life and show how half-life is related to the rate constant, specifically for first-order reactions. What is the definition of half-life? Half-life is the length of time that it takes for half of a reactant to be used up. Let's look at a specific example. Here we're seeing a concentration versus time graph for a first-order reaction. In this case, the initial concentration is 1 molar. The half-life would be how long it would take for the concentration to drop from 1 molar to 0.5 molar. In this example, it would take 12 seconds. How long would it take for the concentration to drop by half again? In this case, since we're starting at 0.5 molar, how long would it take to go down to 0.25 molar? We see in this case that it again takes 12 seconds for the concentration to go down by half. This is a general result for first-order reactions, that the length of the half-life is independent of the concentration, although it is different for each reaction. Some reactions proceed very quickly and have half-lives less than a second. Other reactions take very long and can have half-lives of minutes or even years. Let's show how the length of the half-life is related to the rate constant for the reaction. Since this question is asking about how long it takes for the concentration to change, we need to look at the integrated rate law for the first-order reaction. If we recall, the integrated rate law for a first-order reaction involves natural logs. Specifically, the natural log of the concentration at some later time t is equal to the natural log of the initial concentration minus k times t, again where k is the rate constant. We want to solve this for time, but a specific time, the half-life. We'll label that as T1 half. T1 half is defined as the time that it takes for the concentration to fall to 1/2 of the initial concentration value. So we can plug these into the above equation. Specifically, for concentration of A of T, I'm going to plug in 1/2 the concentration of A initial. I'm going to combine the natural log terms. When you subtract natural log terms, you can combine it into one natural log and make it as a fraction. And when we do this, we'll see that the initial concentration of A is going to drop out from the left side. Natural log of 1/2 is the same as the negative natural log of 2. This is going to mean our negative signs are going to cancel, and dividing both sides by negative k gives us that T1 half is equal to the natural log of 2 over the rate constant k. We see that the definition of the half-life for a first-order reaction involves only a constant, natural log of 2, and the rate constant for the reaction. In other words, it does not depend on the concentration of A. This is not the case for other reaction orders. For example, if we look at zero-order reaction, again, we have concentration of A plotted versus time. And for a zero-order reaction, we saw that this results in a straight line graph. Again, if we're starting at 1 molar concentration, the half-life would be how long does it take for the concentration to drop down to 0.5 molar. In this particular example, it looks like it's taking about 9 seconds. But the second half-life, or the length of time that it takes to go from 0.5 to 0.25, is a much shorter time frame, only about maybe 3 or 4 seconds. So for a zero-order reaction, the length of the half-life depends on the initial concentration. Let's derive that relationship. Again, we'll start with the integrated rate law, but we'll use the one for a zero-order reaction. In this case, the concentration of A at some time t is equal to the initial concentration of A minus kT. Again, we're looking for a specific time, t1/2, which is when the concentration is equal to 1/2 the initial concentration. Plugging that into the above equation gives us 1/2 initial concentration equals the initial concentration minus K times T1/2. Combining terms, bringing this over, gives us on this side negative 1/2 A sub 0 equals minus K T1/2. Dividing both sides by minus KT, just by minus K. K's drop out, the negative signs drop out, and we have that T1/2 is equal to the initial concentration divided by 2 times the rate constant. So in this case, the half-life depends on the concentration of A. You can derive the length of the half-life for a second-order reaction, again by starting with the integrated rate law for the second-order reaction. In that case, you will also find that the length of the half-life depends on the concentration. Pause the video for a moment and see if you can make that derivation. You should have found out that the half-life for a second-order reaction is equal to 1 over K times the initial concentration. The last video in this series will work through a sample problem that incorporates the ideas of rate laws, integrated rate laws, and half-life calculations.